the chain rule. Now, we have incorporated the chain rule into all of our work since we started doing differentiation rules. So we don't need to spend a lot of time on the chain rule itself, but it doesn't help to go through a few extra examples along with a few reminders. In our last video on the derivatives of the trigonometric functions, I differentiated the sine of the square root of x. Okay, and we found that that derivative was the cosine of the square root of x, and I'll write it this way, times 1 over 2 times the square root of x, outside in. The outside function is the sine function. Differentiate that first with respect to its own argument. This doesn't change there. Then times the derivative of the inside function, and we wrote that as cosine square root of x divided by 2 times the square root of x. Well, if we turn it around, okay, again, the sine was the outside function there. Suppose instead we make the sine the inside function. So we write this instead, y equals the square root of the sine of x. All right, same two component functions, the sine function and the square root function, but applied in the opposite order. The derivative is much different, okay? Here, dy dx, the outside function is the square root function. We differentiate that first with respect to its own argument, which is the sine of x. So we have 1 over 2 times the square root of the sine of x times the derivative of the inside function, sine of x. That derivative is cosine x, leaves us with cosine x divided by 2 times the square root of sine x. Outside in. Outside in. All right, so you have to be able to recognize what your outermost function is and work your way in. And again, remember, we may have many more than 2 functions composed. Now, let's take a look at a couple of chain rules with product and quotient rules. All right, so let's take the function y equals x squared times the secant of 1 over x. All right, we have a product rule, x squared times the secant, but within that product rule, we have this chain rule, the secant of 1 over x. All right, so we proceed as we always do. dy dx, the derivative of the first times the second, plus, all right, we'll write the first, times the derivative of the second. Well, the derivative of the secant of u, as we saw earlier, secant u, tangent u, du dx. So we have secant 1 over x, tangent 1 over x, times, and I'm going to put this in a bracket to keep it separated, as I warned in an earlier video, from this, so we're not tempted to multiply, negative 1 over x squared, the derivative of 1 over x. All right, and we can see when that happens that this x squared will cancel with that x squared. This negative sign will replace there. Now we have 2x secant 1 over x minus secant 1 over x tangent 1 over x. If you wanted to, you could factor out the secant of 1 over x. And then you'd have 2x minus tangent 1 over x. Not essential, but always good practice to do your factoring. Okay, and let's try one now with the quotient rule. And here we will have the quotient rule embedded inside the chain rule. The quotient rule in the inside. Okay. And just to get away from x's, for a change we'll use t's. y equals t over t squared minus 4 all cubed. So yes, it's a chain rule. The outside function is the cubing function. The derivative of the cubing function is 3 times the squaring function. We'll start with that. dy dt equals 3 times t over t squared minus 4 all squared times the derivative of the inside function, which requires the quotient rule. 1 times t squared minus 4 minus 2t times t divided by t squared minus 4 squared. So let's clean that up. We have 3. Well, let's do it in one step if we can. Okay? I've got a t squared here. I've got t squared minus 4 squared here. I also have a t squared minus 4 squared here. So on the bottom, I have a t squared minus 4 to the 4th. In the numerator, a 3, a t squared. And from here we get t squared minus 2t squared is negative t squared. So here I have negative t squared minus 4. A rather ugly construction. So let's take that negative, factor out a negative 1, and rewrite that as t squared plus 4. Right? That negative made this negative t squared minus 4 a little bit simpler to write it that way. And there's our derivative, and we're done.